Thank you everyone for joining us. We have this wonderful interview today, and I'm Paul Culette. This is High Peak Education, and it is my absolute pleasure to talk to my old friend and colleague and the Dr. Luc van Roekel, Los Alamos National Laboratory climate modeling scientist, and he's going to be the first, believe it or not, the first guest appearance here on this video channel. So Luc, I want to welcome you and say thank you so much for your time today.
Well, thanks. And thanks for the honor of being the first. See if I can set the bar high.
Sounds absolutely great. And we are recording this, and keep in mind that everyone who watches my video channel knows that I try to make incremental progress and do my best and make things better as we go along. So let me know in the comments what you think about these interviews and who you would like for me to talk to and what kinds of topics you'd like to see covered on this channel. So Luc, I kind of thought that as we've been friends in the past, and as we've been colleagues, and as we've not necessarily had a lot of time together to catch up, I mean, we would kind of start a little bit with some catching up in terms of some of your life and your career. So we crossed paths, as I know, at Colorado State University in Fort Collins, and that's Fort Collins, Colorado. And yeah, I think I was doing a master's degree there in atmospheric science and yourself a PhD. But then after that, of course, we kind of went our separate ways. So could you just kind of catch us up a little bit about how life progressed for you and how jobs and career went forward, and a little bit just kind of catch us up briefly on the story of what led you to Los Alamos National Laboratory?
Sure, happy to do so. So as you mentioned, we were there together. I left in August of 2010. I didn't go too far down the road. I wandered all the way to Boulder, Colorado. So I went an entire hour away to work with Baylor Fox Kemper, who's one of the giants in ocean modeling, and had a great experience working with him and NCAR, which the National Center for Atmospheric Research is there. So I was co-placed between the university and NCAR, which was a really nice time. And during that time, opportunities arose. You know, for those who don't know, postdocs are kind of the training ground for a future career. You go in this, you're still mentored by someone. They sort of direct you which way you should go. And so I had in my mind, you know, I'm going to go be a professor somewhere. So I started applying for places and ended up getting a position at Northland College, which, for those of you who don't know, which is probably many, it's very far north in Wisconsin, right on Lake Superior. So really gorgeous scene. Tiny school, something like 700 total enrollment, and basically was running the entire meteorology department there, with a little bit of help from physics professor, a chemistry professor, and then actually we also had adjunct staff of a broadcast meteorologist was adjunct staff as well. So it was really great. Ended up just finding that it was too much for one person. No man is an island, and neither am I. So started looking for other things. Just kind of thinking about a career reset, you know, maybe to go less from a teaching institution to more of the research side. And thought, well, maybe I need to do a postdoc, because I wasn't catching on with these bigger schools, probably saying, where's Northland College? I have no idea. It's hard to get the attention of someone and say at like University of Colorado when they say, I don't know you, and I've never heard of your school. So started looking at other opportunities, a second postdoc. And the amazing story to me is I never looked myself for the job that I started with at Los Alamos. I had a good friend who was I don't know if he was not the senior pastor, but I don't know what his title was. He was one of the staff pastors in northern Wisconsin. And we would get together and chat every week. So he knew all about what I was interested in. And he said, oh, here's this job opportunity you should look at. And the funny story is, it turns out the person who the job was with, the mentor, used to be in Dave Randall's group, who I was with at Colorado State. So it all comes full circle. And so moved out here, did the postdoc for a while, became staff something like 3-4 years ago. You know, kind of worked up faster than I ever expected to co-leading development on the model for prediction across scales ocean, which is our ocean model, and getting onto leadership of the E3SM project in a number of ways. It's kind of taken off way more than I would ever expected. But that kind of brings us to here. And now I'm in my COVID office. So.
Wow. That's, yeah, quite an interesting story. You know, I definitely find the more years that I'm on Earth, that indeed it kind of is a small world, that you find that there are certain people that serendipitously sort of come your way, or you talk to, or that an opportunity that's really the right thing for you comes about in a completely unexpected way. And it's really interesting to kind of have some of those things happen to us.
Yeah, exactly.
Well, awesome. Thanks. So the second thing I wanted to ask you to kind of catch us up a little bit is, I mean, I do remember that at Colorado State University, a mutual colleague of ours named Pete Rogers used to call you Luke the Math Man Van Roekel. And so the reason I bring this up is because, I mean, I know that your background, like say as an undergraduate, was that I think you were doing like a math degree, and then now you're already sort of atmospheric science, climate modeling, and that sort of route. So could you just kind of tell us a little bit about how, you know, your current career has sort of flowed out initially from like kind of those math skills, and kind of how you use math skills as part of, you know, kind of some of your daily job and everything, to kind of encourage anyone who might view this?
Yeah, I would say if I go all the way back to the beginning of graduate school and thinking about, you know, going from a, let's call it fundamental field like mathematics to more of an applied field like atmospheric science, I believe very strongly that the mathematics unlocks your potential to these other fields. Like, I certainly didn't have the background of the terminology as others did coming into the field, but I knew the underlying math. So once I grabbed that terminology, I was ready to go. And I think for many, understanding the math is a whole lot easier than learning new vocab words for something. And you can see those connections. So, I mean, math and teaching in Wisconsin was not a lot of it. I mean, we did things like dynamics. So we taught, like, how do you derive the dynamics equations, you know, the Navier-Stokes equations for those who are in the know. So we did some pretty advanced calculus. I'm not sure anyone understood it but me. The students did stay awake, which was good. But I mean, here, when you're in the modeling field, the computer doesn't know what to do unless we tell it what to do. So we need to show it what the math is. So the job now is a little bit different, but you need kind of everything, plus like a translation degree. You need to know the calculus, but you also need to know how to take that calculus, say some derivative, a nice simple derivative, and tell a computer, how do I compute a derivative? Because a computer doesn't know. It only knows ones and zeros. So you have to use that. So I guess that's kind of a field that it's like discrete mathematics. So most of what we do is translating calculus to computers. Not many of us get to take, you know, our old dynamics professor, Wayne Schubert, the paper and pencil route, where you're cranking everything out and doing the hardcore, really advanced calculus. Although we do have those at Los Alamos. I know those out there probably think of, when you think of Los Alamos, you think of like the old guy in the sweater and the crazy hair with working on the chalkboard. Those people still do exist. They're still there. but they're less and less. I mean, more and more computational work happens. So it's every day. There's math every day, and having that strong foundation is really essential.
Yeah, that's really interesting. I find because I mean, I think I'm actually working this semester as part of High Peak Education with someone in discrete mathematics, and it's really interesting some of the things that I've learned in working with her because, yeah, basically a lot of the mathematics that I learned to prepare to become an atmospheric scientist, she's just going into more depth to really like understand kind of how like a computer would understand something that I also understand. And
Right.
yeah, I think there's definitely, like you say, there's a lot of kind of terminology that goes along with things when you get into an applied field. And I think part of what comes to mind for me is, I mean, certainly when you're working in an applied field, I mean, part of the reason we do application is kind of the relevance, like the relevance of, you know, you're doing these applied things, whereas like somebody that does something theoretical, like you say, there's people still exist on the chalkboard. That's really interesting to hear, but at the same time, like again, like the relevance is kind of like how much of an impact is there and how much funding is there and how much can I make a societal you know, difference. I mean, I think that's some of what you're saying.
Yeah. They always think that. I mean, at a laboratory like this, we exist to serve the nation. So everything at the forefront has to be, how does this make an impact? It can't only be, am I having fun? I mean, the ideal, right, is you're having fun and you're making an impact. That's what you really search for in life. But you got to find where that is, and it may not be at Los Alamos Lab. So
Yeah, really interesting stuff. And thanks for these great answers. So I'd like to switch gears just a little bit and ask you a little bit more about kind of going a little more general about what you do in terms of climate modeling, and then get to a little more specific in terms of, yeah, basically what's going on specifically in your research group and your research. So yeah, I mean, kind of as you know, like I have a lot more background personally in my career when I've done numerical weather prediction, computer modeling, atmospheric science simulations, whatever exactly you want to call it. Mine's more so in terms of the atmosphere and then in terms of local area models. So those would be things that are most often characterized mesoscale. So things like MM5 and WRF are very common examples of those in the atmospheric science field. But I mean, I have less personal experience for sure running or getting into the guts of what is in a climate model and what is under the hood, so to say. So could you tell us about how like climate models are similar to weather models, but how they're different, and what kinds of special considerations do you need to take into account for a climate model as opposed to like a weather model or a limited area model?
yeah, sure. I mean, so at the top level, something like WRF, the Weather Research Forecasting Model, I think is what it stands for. It's been a little while. But that model is really focused in on the atmosphere, as you said. But if you take, say, WRF and compare it to the atmosphere inside of E3SM, which I don't think we've said is the Energy Exascale Earth System Model, is what the E3SM stands for. Really, that atmosphere inside is going to solve the same equations. It's the same math. The real critical thing in terms of math, and then we'll kind of blow out a little bit high level in climate modeling, are the scales you're interested in. So if you're interested in, say, like a giant mesoscale convective complex and just forecasting that over the Great Plains for 3 days from now, you wouldn't want to use our model. It would be terrible. The biggest reason, probably I would say, is the important structures inside that convective complex are smaller than our grid boxes. So the model just can't see it. So that's one thing. It's what scales are you interested in, what can you afford? This is another big thing, you know. So people may not be aware, we have these massive computers out there. We're not running on, you know, like a few computers hooked together. We're running on machines that are greater than 100,000 CPUs. So very large. The Department of Energy has some of the biggest computers in the world. I think we might be #1 in the world again, or we may have lost it again. It goes back and forth between the US and China all the time. But either way,
that, if I can quickly interrupt, kind of that top 500 website that you can look for.
Exactly.
Yeah. And by the way, I will link to several things we talk about. I will link to in the description of the video, so you can kind of check those out later. Thanks.
It's a really good thing to look at. It's kind of cool to see because it fluctuates all the time. You got systems moving up and down all the time. But even on those, like if we wanted to, so we just started, this is maybe skipping ahead a little, but I think relevant here too. Within our project, we started this ultra high resolution effort where the atmosphere is going down from a climate resolution, which is going to be 100 kilometers on a side. So those who are more familiar with latitude, longitude is about 1 degree in each way. So if you think about your experience watching a storm, say, that storm's usually not 100 kilometers across. Especially like the standard pop-up thunderstorms are going to be maybe 1 kilometer across, and we're just not going to see them in the model. So that's a consideration. But now we're coming down with this project to 3 kilometers. So we're getting close to actually resolving the clouds themselves in the climate model. But as we do that, you can imagine that if you were just imagine in your head, you know, you're going and tiling the Earth with 3 kilometer squares. Just picture how many squares that is. That is a whole ton of squares. And so this gets super expensive. I believe, I'm going to estimate here, but they are able to fill up an entire supercomputer with one of these simulations. And 10 years is going to cost them something like somewhere on the order of 100 million computational hours to run 10 years of simulation. So it's a massive number. So that's something we have to balance. So we have this model of the atmosphere that's, we're going to say, the same as experience with like forecasting models. There are other peripheral differences, like we don't include data assimilation because we don't have observations for the future. And we also have to consider what's below our grid box, what's inside each grid cell, and how do we represent that. But the bigger difference is that we also care very much about what the other parts of the Earth are doing. So we can't just say, let's predict the atmosphere and let's impose some surface heating, let's say. We actually need something that tells us what's the ocean doing, what is the sea ice doing, what are the rivers doing, how does the water flow over the land. These are all considerations we have to make. And so these other 4 pieces form their own components, just like the atmosphere is a component. And then sitting on top of those 5 things is something called a coupler that sends fields like temperature, moisture, wind speed back and forth between the pieces. And so we have every aspect from, trying to think what it'd be the bottom of the ocean to the top of the atmosphere. Not the actual top, but we don't go we go to 60 kilometers, I think, so well into the stratosphere, which is for the layer directly above the layer we live in. There's a lot of important structure up there that we care about very deeply. One of them people may have heard of is the ozone hole. So we really want to have a handle on that as well. And then over the land, I believe our land model goes a few meters deep. So we actually model movement of water through soil a couple meters down. So we don't go into like solid Earth geophysics type stuff. We're near the top, all the way to near the top of the atmosphere. So that's a lot of stuff to say. The models themselves are kind of similar to atmospheric models, but they're all stuck together and they feed back onto each other.
Gotcha. So there's like you're saying, there's so many components that are coupled together, and there's so many pieces that are talking to each other. And I mean, it sounds like you're saying that, I mean, I didn't realize that it goes so deep in terms of the ocean, so high in terms of the atmosphere. And I know people argue about like what's the top of the atmosphere and everything, but like you say, it sounds like you're saying that, I mean, if you're using hundreds of thousands of computers, one of the greatest computers in the world, I mean, even if that's not able to capture small scale features, then yeah, there's certain trade-offs in terms of memory and runtime. And I mean, man, it just sounds like it has to be a big collaboration of many people that really know
Indeed.
a lot about a lot to do this well.
Climate modeling is definitely an enterprise level effort. So our project, which aims to be a little bit like things like the European Center for Medium Range Forecasting, whatever the acronym is, I don't remember it exactly, a modeling center, let's say. We have the equivalent of roughly 60 full-time scientists working on this. Not all here in Los Alamos, but spread across nine separate national labs. We missed 2. We have almost all of them covered. I think we're short 2, maybe a few more. So it's a large effort. You need people with expertise in the atmosphere. You need people in the ocean, all the components, but you also need people who are really good at understanding computational performance. Because you need to work with them to say, okay, I know how to make, this differential equation or this derivative in the computer, but I don't know how to make it fast. I need to go talk to this person over here who does. So you have this huge collaborative enterprise.
That's really interesting. I mean, how you say, and using that word enterprise, because man, that's definitely what I found. I found that nowadays, one of the greatest skills that I often say to students when I'm working with them in education is that they need to be able to understand where someone else that is trained in a different field is coming from, and sort of be able to talk to one another and be flexible, yes, be open, just willing to learn, willing to continually spin up and put pieces together that work together.
And that's words for life. I mean, being able, what is the phrase? Walk a mile in someone else's shoes or something like that. But yeah, exactly. I mean, it's kind of fun too, but you need to be able to go and talk to a computational scientist, and then I need to go talk to a land modeler. Like if you go through my day, it may start as something like, okay, in the first meeting, I'm going to talk about the stratosphere and the quasi-biennial oscillation, which is this flipping of the winds, something like 15 or 20 kilometers above the surface. And then, I'm going to go talk about the Atlantic meridional overturning circulation. Now we're talking about movement from, heat from the equator to the North Pole down to the deep of the ocean. And then maybe we're talking about convection in the atmosphere. And so you're moving all over the climate system. But I mean, as someone who really enjoys science and understanding science, that's exciting to say, I'm all over the place. And sometimes, your brain kind of goes all over the place, but you need that ability to keep changing and keep growing.
Awesome stuff. Awesome stuff. So I'd like to, again, get a little more specific then. You kind of mentioned a lot about how the E3SM works and the components and everything, but I'd like to back up and ask you a little bit about, I feel like it's albeit limited understanding of climate models is that one of the things they are really struggling with, especially in terms of future predictions, is where are the clouds, how many clouds, what are the depths of the clouds, what's the radiative effect of the clouds? And of course, I'm coming from the atmospheric perspective, but I'm wondering if that's still like very much a problem to your knowledge. And then what are some other things that we should know about, like in terms of, real issues that climate models have trouble capturing?
Yeah, so you're right on the money. I mean, if you were to go to, let's see, it's the 6th assessment report of the Intergovernmental Panel of Climate Change. and you look up projections, and then they do a really great job of going down the line and showing, here's a process, here's the error bar, next process, so on and so on. You'll still see clouds and radiative impacts still number one. And it goes back to what I was saying before, that they're just not resolved, right? So we have to figure out what their impacts are based on things the model sees. So given a stacking of temperature, what we call a distribution in the vertical, and moisture, and I guess condensed species too. So we think about temperature. We also think about moisture, which is vapor, but we also want to think about liquid droplets and then frozen liquid. So we've got all these different species in the atmosphere that are complicated. Making this even more complicated are aerosols. So these are the little dust particles, pollution, all this different stuff. Because if you look, that's really hard because there's a lot of impacts from an aerosol. One of them is you could just have an aerosol and the sunlight's coming in and it bounces back out. So you have like a direct effect. You also have indirect effects that, this aerosol could float along, find some water, and all of a sudden they get together and they make a cloud. So that's an indirect type effect. But we also have other much more interesting effects that are outside of clouds, which really are a resolution problem, I would say. And it's such a huge range of scales, it's not surprising, because you have to go from aerosols to the cloud scale to the model scale. And these aerosols are micrometers, so like human hair width, up to, kilometer to 100 kilometer. That's hard. That's a tough problem. But these aerosols also have another effect, that they can move toward the north and south poles, mostly the North Pole right now. And they can settle on top of ice. And this black carbon in particular can create massive changes in aerosol. So absorption of the ice could change. It could melt more, it could melt less. It's hard to say because aerosols are tough. And it's kind of an emerging problem, an emerging capability, I should say, within climate modeling, is to actually model, say changes in species within the atmosphere as the model's running along. I mean, that doesn't even get into the future projection assumptions. Like, we don't know what people are going to decide. So it might be interesting to know that, most people, I would say, I'm not going to say everybody, are familiar with what's called Working Group 1 of the IPCC, that governmental panel. They produce those, here's how much it's going to warm type things, or where it's going to change precip. But there are also other working groups too. There's one that looks at the economic impact of climate change. There's also one that designs these pathways for like carbon dioxide and things like that. So they have different types of models that are way outside my expertise, so I'm not going to talk about them, but they're what called decision-based models. So they say, like, well, if the climate's going to warm here, it's likely that we're going to change this crop type to that crop type, and then it's going to change the emission of carbon to the atmosphere by this much. Or what if all of a sudden we all decided to put out solar panels? What would that change? So that's how they generate these scenarios, and they go through and say, well, let's just assume we do the same thing we're doing now. That's usually one of the scenarios, called the business as usual scenario. And you could say, what if we get worse? Or what if we get better? Or what if we get really better? Like, I think there's a scenario that allows you to go out and like just carbon emission goes to almost zero really quick. So there's a super high end one. So that's a lot of uncertainty too. And this is why we run all of them when we make these projections, because we want to capture what's called the spread of the model variability. So this is the word we use are ensembles. Ensembles are critical to our field because going way back into the atmospheric literature to Ed Lorenz, he was the first one to find, and maybe you've talked about this before, that you make these teeny perturbations to your simulation and it winds up in a totally different area. Whether the butterfly flaps its wings in somewhere and there's a tornado in Texas, I think is the usual analogy. So we have the same problem. So what we need to do in climate is we need to run enough we could almost call them versions of the climate that we perturb it, 15, 20, 30, up to maybe 50 times. And we run them forward. And what we expect is them to kind of wiggle around as they go forward, but they're all going to go in the same direction. The way we get away with this in climate, where you can't in weather prediction, is climate is an externally forced problem. The weather is often very highly dependent on, like the internal variability. But since we're so dependent on solar, on the carbon dioxide, it's a pretty strong control on where the model's going to go. So we can find an ensemble mean. We take all those things together, collapse them together, and we can figure out which way it's going to go. But it's important to capture the broadest range of states we can to give us more confidence. Hopefully that wasn't too rambly.
No, really a lot of great information. And I'm sure that as part of the video, I'll be able to link to a lot of cool resources. I mean, you mentioned how to deal with, high sensitivity to initial conditions, which I know on my channel, I've talked a little bit about differential equations and how highly sensitive they are to initial conditions. I mean, you kind of mentioned Edward Lorenz, and I mean, really in terms of, chaos theory, I've heard it. I remember reading in the book by James Glick called Chaos, he talks about how, people just would not have expected this to be sort of, discovered or uncovered by an atmospheric scientist, published in plain sight in the Journal of Atmospheric Science.
Right.
And yeah, so really interesting stuff. But then also, like you said, there's so many of those working groups, I guess I wasn't aware of. Like you say, I'm a lot more aware of, kind of the stuff that's most popular that everybody hears about in terms of the scenarios, the business as usual. What if we have a carbon tax and all these kinds of things? And yeah, absolutely. But wow, decision models and changing land use and oh my gosh, it sounds like you're saying that basically, since you mentioned earlier in the interview, the Department of Energy kind of, how do you say, wants to really serve the public. It sounds like they're really, really trying, and you're certainly aware of, and even your research and group is doing so many scenarios over those ensembles to really kind of cover the gamut of all the different things that could happen and really try to get some average and some uncertainty spread on what are the possible scenarios.
So let me say that's an aspirational goal for us. We're not there yet. We're a relatively new model. There are others. Probably the one some people may have heard of is the Community Earth System Model, which is from NCAR. They've run some iteration of that since AR Assessment Report 1. We made our first contribution, a partial contribution to AR6. So we're a very new project, but our goal is to get there and to not sit at sort of the IPCC, let's see what happens by 2100. Our goal is more like what happens in 10 years, let's say. And what makes that especially tricky is you're getting into this place where you mentioned, sensitivity to initial conditions is a problem. That's true for forecast models all over the place. And if you go long enough, the Earth kind of forgets about the initial condition, and you can do almost anything, especially for these strongly forced problems. But when you get kind of in this gray zone where it's not quite a boundary problem, where it's the forcing and it's not quite initial condition sensitive, it's hard to know what to do. So it's especially interesting. Yeah, so we're getting there, but the goal is sort of what's going to happen in a decade or a few multiples of decades.
Yeah, interesting stuff. You kind of already mentioned a little bit about how E3SM is kind of a newer player in this game. I'm just not sure if you'd like to say a little bit more just kind of on this kind of last technical part of the talk here in terms of what is it, say even a little bit more about what you and your research group does, and then how E3SM is unique amongst all these players, because you've given us a lot of great stuff.
It's important to me because the question you're going to get from For those of you out there who are thinking about, I want to go be a scientist, one thing you have to think about is who's gonna fund me, and how do I get funding? It's a competitive game, and one of the first comments, let's say, you're going to get from someone is, why do we need another climate model? If you look in the assessment reports, there's 20 plus climate models. What are you doing? We are not interested in that same game, kind of the same game, where we have to do that because that's what the community does. We need to show that we give high fidelity, great accurate answers relative to the community before we can do something different. So being the Department of Energy, our interest is going to be more on the shorter term, and we're really focused in on North America. We have a huge interest in that. You could think about, there's a lot of things you could think about. One of them is, how is the water availability going to change? Are we going to end up locked to giant drought and all of a sudden water is going to be scarce? You could get even more specific to Department of Energy and ask questions like, what if the watershed start to evolve and you've got these nuclear power plants that have cooling areas and all of a sudden your water's gone? What do you do? Or you could be pretty practical and say, well, I'm kind of interested in all this coastal infrastructure, roads, bridges, power plants along the coast. What happens if the sea level rises? How likely is that? And there's certainly, another big one would be like transportation. You think about the Northwest Passage, this route through the Arctic that used to be open but is no longer. It looks like it might open again. Shipping companies really would like to know when, if. That's going to have big impacts. Geopolitical as well, which won't get into here. So let me say, when we think about North America, if we are just like the other players in the game, where they say, I have to set down grid boxes everywhere that are pretty much the same shape, except for when you go to the pole, which induces other problems, because you can imagine as latitude and longitude comes together, your grid boxes get 0. And you have to do tricks like rotate latitude and longitude such that poles are in different places, or turn the Earth into a cube instead of a sphere. There's all kinds of tricks. But what is super unique about E3SM is we've gone from this structured approach where we know exactly where the grid boxes are all the time. And we lay it down at the beginning. They're almost the same size. That's what's called a structured model, a grid model. So there's been new advances that we are leveraging that move us to an unstructured model where we don't know in advance, what the resolution is. And really nicely, we can just decide where we want resolution. We could say, within, let's say, 1,000 kilometers of North America, I want to be storm resolving. So this would be something like 25 kilometers on a side in the atmosphere, probably 10 kilometers in the ocean. We can do that. And then outside of that, we can coarse it out to 100. So it gives us a huge computational savings because we just don't care, about resolving all the teeny tiny features outside the box. So E3SM is the first model that has this capability in every single component: the atmosphere, the ocean, the land, the sea ice, the rivers. That's the other one. I know I forgot one. We got there. So that's really unique, and it allows us to start to answer these these US centric questions, whereas others are going to have a harder time doing that. Because if you took, say, CESM, and you wanted to do a coastal impact study, you'd probably have to have global resolution of a few kilometers. Now, actually, they can kind of do that. There is a project within CESM to run these super high, like a 10-kilometer-ish thing, but it's really expensive. So E3SM is really built with North American questions in mind.
That's really interesting stuff. I mean, I remember, I've had similar numerical modeling courses to you, and kind of how you say you can go from structured to unstructured, that flexibility thing we even mentioned briefly before. But then, yeah, being North America focused, also being able to kind of drill down on certain questions. And yeah, that's really some interesting stuff. So that's cool. That, I mean, I think one of the things that you asked me about before we started talking on the recording is like, how things are going for me. And sometimes people often ask the question, well, why are you getting into a certain field, or why is there's this new model? But sometimes it's that there are a lot of solutions to a problem because there's also a lot of opportunity. In other words, there's like a lot of market for maybe doing things in a different way to kind of leverage value out there. So I think you did a great job explaining like
Exactly right.
how E3SM really provides value that other climate models really don't have.
The other thing we're adding that I did not mention, but people may be interested in, you've probably seen these dramatic videos of Antarctica, like, giant chunks of ice falling off. I mean, it's a terrible thing. But we are also working on one of the first capabilities, not quite the first, but of having land ice models in the Earth system and actively communicating. We're driving toward allowing these chunks to break off as the model runs to, this is called marine ice sheet instability, to try and say like, well, if we go along pathway 1, say business as usual, how likely is it that giant chunks are gonna fall off? And what does that do to sea level? So it allows those newer questions to answer. But that's a little bit longer aspirational, but work that's ongoing.
Wow. Yeah. I remember I was actually, just a slight anecdote, but I was a teaching assistant for a climate change class at CU Boulder. And I remember us discussing how if you get huge changes in the sea ice, like you have this idea of, suddenly there could be sudden shifts, and then all of a sudden you have like these non-linear effects, and how all this ice starts sliding around in like a way that like wasn't originally predicted, and how crucial that is, and that sort of thing. So yeah,
ice is pretty wild to think about. The way you model ice is very different from how you would model the atmosphere or the ocean. Actually, sea ice has often been modeled as a pliable plastic sheet. Actually, they use some advances from material science to actually model the sea ice. There are changes, of course, but basically it's called the rheology, which is the structure of the ice, is modeled after viscous plastic interactions. So it's definitely a different problem.
Wow. Yeah, you said so many things in our chat that I feel really interested in and want to just look up and learn about. And it's funny, I mean, as a person who really loves education, I always just think, oh, now that Luke's mentioned that, I really want to go back and understand that, because that's always the perspective I'm coming from. I really want to understand, and I just know that, oh my gosh, it's just, some of these things are so vast to really get into understanding how these modeling processes work. Yeah. Awesome. Well, a couple more question. You kind of already mentioned a lot about impacts of climate change and what you're kind of doing. So I just wanted to ask you, if you wanted to say a little bit more, you have the floor, about what you would hope that, given what you've already mentioned, what would you hope that people who are wondering about climate change and wondering about climate models, what do you wish that they would know about the promise, but also the limitations of climate models, and kind of how they should make decisions on those?
Sure. So anytime we get toward impacts and decisions, it's very important for me to say everything I say in this, really everything, is not in any official capacity as a representative of Los Alamos National Lab. Just a standard disclaimer. The one thing I often hear is, well, we can't predict the weather 10 days from now. Why should I trust a climate model for 50 years from now? And the example I like to give people is it's first a different problem like we talked about. It's not initial condition limited anymore. And we're not predicting the same level of detail. So we're not saying in, December 15th of 2051, it's going to be a daytime high of, 50 and a low of 10. What I can say is, even if I didn't have a computer, I could tell you in 100 years from now, December in Colorado is going to be colder than July. I mean, so we can make future predictions, right? It's just what we actually predict. So climate models know things. They are very good at what they do. So we can take confidence in them. We have made, even if you go back, like you could say, well, when you started this enterprise in the 80s or whatever year it was, in the first assessment report, I wonder how that looks. It turns out climate model projections have been pretty good for a long time, if you look back. And again, that's the reason, because this is a strongly externally forced problem and models can handle that. The other thing that people can know is that, we have these different climate models, and we don't have 20 or 25 climate centers. We probably have close to 10 around the globe that are actively developing climate models. And we're not copying each other's papers, we're all developing models that are really, really different. And it is amazing that, we're converging on somewhat of a common answer. So this is similar. You could think of this kind of like proxy records. So how do we know what climate was like 100,000 years ago? We can look at ice cores and things like gases in the ice cores, coral reefs, et cetera, sediments. And any one of these, this is not a great analogy, but it's close. Any one of these taken in isolation, you wouldn't trust. But since you have, 4, 5, 6 wildly different methodologies for predicting what it looked like, and they're all giving you the same answer, it gives you a degree of confidence. I'm not saying that climate models are as inaccurate as looking at the isotopes of oxygen in an ice core, but it's kind of the same thing. We have different models giving you a similar answer, so it gives you even more confidence than you had before. So we know things about the climate, but we also have limitations, right? And we admit those. We would never be so bold as to say, we know in, I don't know, pick a year from now, 2030, let's say, that the summer is going to be exceptionally dry. We would never say that because we don't know that. We can tell you that something like for the period of 2030 to 2040, it's going to be on average drier. Because we could do these types of things. You get enough of these ensembles and you get robust enough statistics. So we essentially have all these different, what we call a realization of the Earth, that when we do statistics on them, we trust the mean. And those out there who have looked at some of these IPCC plots, you will note sometimes that, it'll have a map of the Earth. It'll be some field, let's say temperature. And some regions are going to have like this little cross hatching in it. Those are the regions we most trust, right? So these are things that we call are significant at the 95% confidence level. That means there's only a, 1 in 20 chance that it would randomly happen. And we also know with near certainty that humans are causing the problem. So the way we do this, we take our models, and these are great laboratories. We can't do this to the Earth, obviously, but we can go and we can extract all of the carbon we've dumped into the atmosphere for the last, say, 100 years. And we run forward. And if you look at globally average temperature, it goes straight flat across. As soon as you put in the CO2 injected, which has to be anthropogenic, it's where it comes from. The other portions are recycled, right? So anytime a tree dies, it's going to release CO2, but it's going to be taken up by the other trees. So this is stuff we're putting in. So, and then we just like beautifully reproduce the temperature record. So we know that humans are making a difference. But what we struggle with on the scientific side is telling relatable stories. I could say, if somebody sees the Paris Agreement out there, and again, we always have to say, this is not for the citizens in Paris. This was signed in Paris by many countries from around the world, and heavily negotiated. You'd say, well, they're really trying to get us under a 2 degrees Celsius warming. That doesn't sound so bad. You'd imagine there are some days during the year, like, I would kill for 2 degrees extra. Another 5 degrees Fahrenheit would be beautiful some days. But it's devastating to to wildlife. It's devastating to sea ice, because this is a globally average temperature. What that number doesn't tell you is that could be upward of 10 degrees in the Arctic, and you could lose all of the ice, all of the fishing from the, gotta get right, the Inuits would be gone. They would be decimated. And you'd have new things, like you'd have waves that come up on the coast and you start to erode the shore, which has never happened before. You also start to warm and the permafrost melts and you have methane release, which accelerates the whole problem. So there are stories to tell that we honestly don't always tell so well. So that's why these types of forums are especially helpful. If you think about not only when you go forward in a career and do science, it's great to get in there and understand it. But like you mentioned before, you got to be able to come back out of your shell or out of your corner office where you're working on the notes and go out and talk to somebody and say, this is why you should care. It sells yourself. It may change their opinion too. So it's all really important.
No, I love that answer. And by the way, I have to briefly say anecdotally, here in Colorado, we're expecting a high temperature of 11 degrees Fahrenheit on Sunday. So, I mean, basically like 2 degrees warmer on Sunday would be fine for me, but I certainly know what you mean on average globally and otherwise. And yeah, I mean, wow, I really love how you said that there are stories to how the climate affects everybody. And I appreciate you, kind of attributing some value to just forum and just like the channel that I have, because yeah, basically what I'm trying to do is I'm trying to make things communicated to people in such a way that they can understand it and it's relevant and it's interesting and that they can learn, and it encourages them to either, if they're going into science, to pursue it with gusto, but even if they're sort of not going into science, to really investigate and to learn and be educated and make good decisions. Because yeah, I mean, an informed public is going to be one that really makes good decisions in terms of for the good of us all. Absolutely. So I think we're about coming up on the end, and I want to thank you for your time. But of course, I have to ask here at the end, kind of the important conclusion. If you're still, even though you're kind of in the southern United States, if you're still staying a strong hockey fan, given that you got your roots in the upper Midwest.
Yeah, that gets hard to do down here in New Mexico. I mean, we do have, I don't know what the ranking is, but we actually do. People will be surprised by this, but we do have an outdoor skating rink here. It turns out to be down in the canyon, so it's a little bit colder. So we have a little bit, but it's hard to track, right? Because we don't have, I think New Mexico is one of the only states without professional sports of any kind. So it's hard to see it. So it's kind of fallen off, unfortunately. Whenever we get those, though, like the outdoor games they have, like on New Year's Day, the National Hockey League usually does, right?
Yeah, the Winter Classic, is that what it's called?
Yeah, thank you. That's what I needed. Yeah, that's always fun. But to actually follow a team, it's more like, oh, it's on, I should watch. But I mean, it's been really wild to watch like the playoffs this season, and then them starting a new season where it's just totally empty arenas. But I guess it's worked. I mean, I've been really impressed by the ingenuity to get things to happen. So it's harder. And, when you have all these different interests, it's hard to focus in on on other things sometimes.
So Dr. Luke had to go, but I want to thank him so much for a wonderful interview and for his time. and I want to thank you all for watching this first interview of High Peak Education. You can find links to the E3SM in the description of this video. You can also find information about the Climate Model's Twitter handle and things like that. Please check out the cards throughout this video up here and the links in the description, because I'll link to several videos that I cover topics that we talked about on this channel, and then also some external links which will help you go even deeper. So thank you for watching High Peak Education. Please smash that like button if you enjoy this content. Please let me know in the comments how you're going to use this and how this is going to be new useful content for you. Please, social media links are in the description as well below. Please follow us on social media. Please support us on Patreon. I look forward to seeing you in the next video.